Okay, 10 o'clock. Before I start Monday morning, I'm gonna announce a couple of things. You're supposed to distribute the probability models, right? I'm pretty sure. Jungan, you're the new person, so you have to start over, starting today. But I'm pretty sure you get the email from Higyu. 8-page probability model. I really summarized 6 probability model. And if you look at the last page, I gave an assignment. I said mini bi-weekly project, but don't be really struggle when this semester I try the new approach for homeworks, project, whatever. Don't be confused. Nothing too much worry, because this is new approach. I felt this is rather innovative idea that you can really think, okay, and not just looking for one number. So that's the whole idea. Bi-weekly, I said the due date is September 30. September 30 is Friday, isn't it? This Friday, so not appropriate. So let's push down to Friday next week, okay? And also, everybody has this set. Everybody has it. Yes, you have that set, probability model. And the second page, you have the probability actual curve. So you have it? Who cares? I said, here is a 6 model. First one is a log normal distribution, then gamma distributions, and has Rayleigh distribution, chi-square distribution. It's all different model. You know, we have 11, 12 students. You know, each person is not all same looking. So same thing. This has a skewness in the system, non-zero kurtosis and all that. But I said pick out the log normal distribution, and I said 2 additional distribution from here. Then really work out in your area as possible. Then fit such a model just to practice. Because later part, if you have to really generate the model yourself, geez, how can I do that? How to fit this model into my experimental data or analytical data, vice versa. But let's reduce a little bit. One log normal distribution, use it. I clearly indicate select log normal, and I said 2 additional probability model freely. But let's pick out log normal is a must. It's really, really nice non-symmetric distributions, okay? And also log normal plus 1 additional. It's very similar, as you will see. All 6 models, of course there are more than 6 models, but I give you 6 models to introduce a different model. But select the total 2, okay, rather than 3. You follow me? You follow me? You know, one time in the States, I had English class some 40 years ago. Then teachers really, at summertime, teachers explain all this. Then she asked me, Mr. Shin, do you follow me? I didn't follow you. Follow means chase around. You see the point? Another meaning is, do you understand? I didn't follow any girls around. You know, that reminded me here. So then just to follow, as I indicate, it's not trying to give you a harder time. I'm trying to give you to think, not just looking for one number. If I give you problems that you're looking for one number, I fed up to see you having one number. So sit down and do that. Okay, so the Friday, next 2 weeks. We have about 2 weeks. So whether I finish this or not, I will finish Wednesday, 6 months. But take a look at all this, okay? Then, of course, tomorrow I will hand out another set for beginning of structure reliability discussions, okay? And still, today I really want to finish the correlation function. Correlation, mathematically very simple, but physical implication, that's what I'm really chasing around to let you understand well. So we discuss, this is correlation. Correlation function is relation between the two random variable, or two or more the variable. So I give examples last Friday in a perfect linear relationship or somewhat linear analytical functions and no correlation situation. No correlation situation may be totally independent each other. So so correlation function, I'm going to talk about correlation function. Correlation function. Correlation is again, if I just draw the plane XY axis, then relation between the Y and simply the X axis. Then when you put the data, believe it or not, some data is outcast always. That's what's happening. Or outcast here. So then to develop the analytical model or probability model, then you have to have a continuous function for this. So let's say, well, I want to have regression. I like to have a regression line. In other words, I want to fit the line here, not the polynomial. Some data set you might have to fit the polynomial, second order, third order, whatever you need. So here we're going to try the regression line. Regression line, as I mentioned, is the best fit. Okay? Least square is a typical one you have done it. And I said, okay, I want to, some more. I want to have, as approximation, I want to have some best fit the regression line and passing through the 0 point origin. You can do that because if it's is origin, if you have to do something like here, you can reset this XY axis origin right at here. So you can always set something like EX Y is equal to 0. That's the mean value, right? You can always set equal to 0. Why? For convenience. Then develop the simple equation set, best fit equation set. Then you can introduce a mean, effect of the means, vice versa. So here I'm going to say this guy is Y is equal to mx. Of course, m is unknown here. We'll let it passes through the origin intentionally to make it simpler. Then how to find the problem to solve is how to find the m, the slope for best fit for the data. Okay. So to do this, you can. I'm gonna write down the meaning here. Straight. This is a straight line approximation. Minimizing the square of the deviation. Deviation is really deviation. It really means the difference between the two numbers. Okay, deviation usually set the deviation as a delta. Delta deviation is y minus mx. In this case, this is a real data set, data number. Over here, I'm going to say this is a data point. So this is the y is equal to mx. I'm going to set that like this. So of course, this is a y point, and this is mx point, and that difference is a delta, which is a deviations, okay? So as minimizing the square of the deviation, square of the deviations, okay? Then I'm going to minimize that. That's the approach, least square approach. And deviation is deviation of actual value, which means is really y in this case, from predicted value. To be predicted, simply speaking. Y is equal to mx, which passes through the point along the line mx. So that's what the delta is, a deviation. Then I'm going to square it. Okay? Square it. So here I'm going to take the average expected value. We have many data points you have to deal with. So expected value is the best choice. is a delta square e to the y minus mx. Now you are in the position to minimize it. Okay, minimize expected value of the delta, the deviation, the squares. And of course, this is the usual approach, but some situation you might want to have same approach, but deviation you might want to have. This is a data point here. Throw the horizontal line. Just a watch, okay? That's all you need. This is x value, and this is x data point, and this gonna be the line pointing in the predicted line. So this can be something like x is equal to my, or you can just use the same thing. Why not? Y is equal to mx, or just to draw the horizontal line rather than the vertical line. I think this would be more appropriate. No, let's use the same thing. Why not? It should be okay too. Then you can work out this direction rather than that direction. But usually our mind is set here as y is equal to mx using that direction. So now we're gonna just open up this because we have to minimize this. How to minimize it? You simply take a derivative with respect to m and set equal to 0. Then you can get the value of the m slope. Then that's what the best fit curve is. So if you do that, then it's just open up, expand inside the expected value. Then this is m. Let's do this guy first, this guy last. So if you do that, so it's gonna be m square x square plus y square. Y square minus 2mxy 2m, correct? Plus y square. Oh, I'm it's Monday morning. M square, and now it's okay. It's correct. Yeah. So now I'm gonna really open up. If you open up, then e to the y square. So it's a minus 2m, because m is a constant, xy, and plus m square e to the x square. Make sense? Yeah. So now we're gonna take the derivative delta x squared with respect to dm set equal to 0, okay, which is really slope of the quadratic equation form, then determine the m. That's what you have to do. So now if you take a derivative with respect to m, this guy is out, right? That's a 0. The first term is a 0. Second term is a 2, the e xy, and plus 2m e. If I screw up, let me know. And that has to be equal to 0. Then if you just cancel this guy out, so now m here is equal to e to the xy over e to the x squared. Determine the y, then you can simply say y is equal to mx. Regression line is gonna be e to the xy over e to the x squared. E to the x squared, e to the x squared, yeah. So we know mean is equal to 0. We know mean is equal to 0. So I can say that e to the x squared is equal to sigma x squared. Can I do that? Mean is equal to 0. We use a symbol, we use a symbol mu x and mu y. And this guy, x minus mu x squared, is equal to e to the simply x squared, because mu x is equal to 0. So you can do that. So you can simplify the equations now. And this also, same way, y squared is equal to sigma y squared. Simplification for solving the problem and adding the effect later before, rather than messing around from the beginning. So from here, I'm going to divide by sigma y e to the xy, and this guy is sigma x squared. I'm going to say sigma y times x, right? If it's wrong, let me know it's wrong. Okay. So next, what I can do is same y, sigma y is equal to e to the xy, and the sigma x, sigma y, and move the sigma x right here and put the x right there. Okay, this is related to the correlation function. That's the beauty here. Okay, so now this situation here, this situation EX, EY is equal to 0. That's what we reset the curve from the beginning, so I can claim that. What happens if mu x, mu y are not equal to 0? Let's say, what happens if it's mu x is not 0, mu y is not 0? Then all you have to do from this equation set, replace x to x minus mu x, and also replace y as y minus mu y from this equation set or that equation set. Then that's the situation for non-zero mean. You can start from the beginning and get the equation, but this is the easiest way. So if you do that, you have y minus mu y over sigma y. Can you see in the back there? Yonghyun, can you see here? From there here? I end up to give you the expression for correlation coefficient and also covariance and the bound of the correlation coefficient. Before, I just give you like rho xy is in the range of -1 to 1. Depend on the correlation intensity. So here, I'm going to just rewrite y minus mu y over sigma y is equal to, replace x by x minus mu x, y minus mu y, sigma x, sigma y over x minus mu x, sigma x. So here, I think I mentioned Friday, this is, what do you call this? This is called covariance. It's a covariance. Okay, that's a covariance. The whole thing, this whole thing is called the correlation coefficient. So here I'm going to say that this is rho xy times, this is times, right? Times. So this is equal to sigma x, sigma y, so which is the whole thing, which is called the sigma xy. You know, I'm getting a little bit reluctant, strictly speaking. This should be capital X and capital Y, and that should be also capital X, capital Y. It has a tendency just to use a lower, subscript as small xy, but you know what. So this is a covariance. Whole thing is called the correlation coefficient. The range of correlation coefficient is -1 to 1. I can just say that's the range, so we'll quickly derive the range -1 to 1. So over here, this xy relationship, x and y, if you have a curve like this, doesn't have to pass the 0 because this is a generalized situation. Rho xy is, of course, is equal to +1 in this case, if this is a 45-degree angle. Okay? Positive rho xy is a positive mathematically. It is falling in that direction. And if it is in that direction, so this is rho xy is -1. Of course, this happened to be 45-degree. And another situation maybe it could be like this, or it could be like that. Then that's independent each other. Rho xy is equal to 0. Rho xy is equal to 0. If the rho xy is equal to 0, no relation between the random variable x and y. It's clear. So that's the range. It could be rho extreme case. The rho xy could be equal to 0, or could be -1 to 1. This falls the between. So lots of situations, in reality, I mentioned Friday, with the non-zero rho xy, is a joint probability density function is getting very messy. Then always getting into the special case, what happens when the rho xy is equal to 0. Then you can estimate all the result nicely. Then really put the dependency as a non-zero rho xy and work it out. That's the way you could see. And if you look at my note, everything is in my note in your handout. There is the situation when you're dealing with the deviation as x minus mx, you can work it out in the same way. No differences at all. And the bound of rho xy, how can you say the range of correlation coefficient is between -1 to 0? If you, like Yun Seok, you're the only one here, and Higyu took the course I usually offer on spring quarter. That's the dynamics of this version. And you remember this? No? Well, that's a year away, last year. So proof. How can you say that rho xy has that range? If you ask me, what does it mean really? It's hard to answer, except just showing like this. Negative rho xy. Think about it. Maybe you can be ahead of me. Maybe Jungan, you're working on the probabilistic the theory also. So, okay, prove, start with this. B y minus mu y, and take the square, take the expected value. Expected value of this function is always greater or equal to 0. Naturally, it's a square. Expected value of the square. Of course, a and b are the real constant. Then if you expand it, so we're going to do just for the completeness, a square x minus mu x square plus 2ab x minus mu x y minus mu y plus b square y minus mu y square has to be just expanded. Then we apply expected value to each terms. So a is a constant, it's going to be out. So x minus mu x squared plus 2ab e to the x, x minus mu x, y minus mu y, plus b squared e to the y minus mu y squared, complete, This is it, equal to 0. So if you look at this, so now this is you called what? Sigma x squared. So it's a squared plus sigma x squared plus 2ab sigma xy. This is covariance. Okay. Plus b squared and sigma y squared has to be greater or equal to 0. So of course, assuming a and b are non-zero, constant, reasonable, otherwise it's a trivial problem. So I'm going to divide this set by b squared. Then I'm going to say sigma divided by b squared a over b squared 2 sigma xy 2 sigma xy a over b plus sigma y squared has to be greater or equal to 0. Of course, assume here surely b is not equal to 0. Otherwise, a trivial solution you could have. To get this value greater or equal to 0, this is a quadratic equation. What's the requirement? To have this quadratic function greater or equal to 0. Greater or equal. So if you look at the like a parabola, if it's go down there, it has a negative value, right? So discriminant has to be what? Discriminant has to be positive. Why? Because you remember this ax squared plus bx plus c equation set here. You know, then what's the root here is equal to 0. What's the root? X is equal to minus b plus minus b squared minus 4ac over, what's this under? 2a, right? You remember? Root? Say yes, yes, but it's gone, but we have to bring it back. So that's the root. But in this situations over here is equal to 0 means this cannot go below 0. Minimum it can go would be like this, right? This is the case when this is equal to 0. Otherwise, it's above the quadratic function has to be above the y is equal to 0 axis. It has to be above this. Right? 3, 4. So we have to do this guy. This guy, the requirement has to be or greater. Equal means it's right touch there, right? Because this is the root. So if you do that, then the discriminant that b squared minus 4ac for that equation is 4b squared. This is what the 2 sigma xy squared. 2 sigma xy squared minus 4ac. 4ac. Sigma x squared. Sigma y. Oh, I'm sorry. This has to be less than. Otherwise, has a root, right? Shouldn't have a root. Hey, wake up. Monday morning, tough, right? So, less than equal to 0. Right. Makes sense, right? Then if you minus value, you square it, it's all positive. So so I can rewrite this guy as a sigma x y over sigma x sigma y. Okay, if you do that, I can draw like this, easy, right? So this guy, what do you call this? What do you call? Rho xy. So bound of correlation coefficient is like that. Question? So correlation coefficient, rather than ranges between -1 to 1, it has a simple proof and is correlated each other. Question? Back there? All right. So today, I think I give you some simple assignment, right? And return after class. Here you can take it up. And also, did you bring the probability model today? My note, probability model. And if you look at the middle, it said review example 2.4. The textbook is a choice book, the red cover. Example 2.4 is on page 27. There is a full description. You have to be careful because some, of course, author makes a mistake. Anybody can make a mistake. There is some mistake. You have to look at it. And probability model. We're going to start. Next few minutes. Mothers. And also example, you don't have to turn in this one, okay? Example 2.4, I want you to solve, go through, think a little bit, then that goes to half, 1/3 of the next page, and I want you to not just to look at it and get the result. Result is correct, okay? And log, no, this is just to make sure you do. Not the homework, just to do it. Okay. And the first distribution is log normal distribution. If you look at the name, it's amazing. Whenever I deal with the probability model, I mention about the probability density function, probability distribution function, or cumulative distribution function. But all such a function, probability function, people has a tendency to call simply normal distribution. That doesn't mean that it's just a cumulative distribution. It just means probability function. Could it be a density and distribution? Distribution is a summation of probability density function. So we are dealing the model. I talked to you already last week. Why we are talking about the model? All I want to talk in the content of the probability is model. Because structure reliability is dealing probability model and dealing with the type of the probability model. And also integration of a probability model. Integration of is not simply fx. It's not simply fxy. It's a multiple, the dimensional, the variable probability density function, and also cumulative distribution function. That's why I keep talking about it. And now this time I want you to get the feel on the model, okay? So first one is a log normal distribution function. What's another one? I just follow the choice book, 3 authors, okay? And the gamma function. What's another one? You remember? Because I didn't start, so I didn't start either. That's right. What's another one? Like exponential function. Exponential function. Weibull distribution function. Rayleigh distribution function. And what else we have? Chi-square distribution function. One more. What's another one? Shall I look at it here? Gamma distribution function, Weibull distribution function, and exponential distribution function, Rayleigh distribution function. Maybe five. But that doesn't mean there exist only 5 models. No. Few more, like a Gumbel distribution function. I'm not gonna bother to go through this. This is all belong to so-called extremal type. This is type 1, type 2, type 3. If you're gonna make another model, you can say Jungon model. I'm not kidding you. You can make it. Has all skewness in there. Looks very similar, but question is which one would fit better? Like a failure probability model for electrical system, they use quite a bit for exponential distribution. Depend on the need. Okay, for the new equipment. Usually new equipment, it fails a lot at the beginning, right? It fails quite a bit. So if I draw the time to failure, here is a T failure rate, or PF. At the beginning, it fails a lot. It fails at the beginning, it fails a lot. Then after, for a while, for the new car, some problem car, like a made on Friday, it's called a lemon car in the state. Why? Because Friday looking forward the weekend activity, so didn't really pay attention much. So Friday, the car made on Friday called a lemon car. Well, that's what. Then it fails a lot. Then after for a while, then it stabilizes. No more failure. It stabilizes. Then what happened? After you use it 10 years, then what happened? It started to fail again. it's time to get rid of the old car, get the new car. So get here, it goes up. Failure rate goes up. So from here, in this region here, is exponential probability function fits the best. So such a situation, this exponential probability model fits really, really good. And for the Weibull distribution, for the gust wind, hurricane, typhoon type of the wind problem, and this is a really much better model to cast into the probability. So that's what one of the, I call them mini weekly, bi-weekly, because it's about time to use the name bi-weekly, but it takes a little bit more time, more thinking you have to do. So that's why I called it that. Okay, so I'll stop here, and Friday I'm gonna finish this model because I'm gonna introduce and characteristics is your job to do. Okay.